Alrighty, hi everyone. We can get started. So welcome to another week of review sessions. More faces here this week. So to reintroduce myself, I'm Allison. I'm your IA. And then I do my review sessions a little differently. I like to work through practice problems during this hour. But I like to feed your questions. So with that being said, are there any questions that we would like to start with? Any topics you want to start with? And then we'll kind of go over it and do some practice problems to help you learn them. Yeah.
Net ionic vector
Equations and stuff. Yeah, absolutely. Alrighty, and then I will be writing on my iPad and everything will be up here. So if you can't see anything, just let me know and I'll write write larger. Alrighty, so can someone tell me what a net ionic equation is? What does that mean to be a net ionic equation? When do we usually talk about net ionic equations? What type of reaction? Yeah, chemical reaction. Is there a specific type of chemical reaction? Right, so usually this is going to be double displacement, right? Double displacement reactions. We tend to be able to write a net ionic equation for. Specifically, we can talk about maybe an acid-base reaction, right? So in this category, we can talk about acids and bases. But then we're also going to talk about precipitate formation. And when we talk about precipitate formation, that's going to be where your solubility chart comes into play a lot, okay? So one of the typical net ionic equations that we talk about is going to be the combination of a strong acid with a strong base. So does anyone know a strong acid off the top of their head? Yep, HCl is a good one, right? We have a proton, and then we have a chlorine ion. So that H plus is going to be our proton indicating an acid. Anyone know a strong base off the top of their head? Close. It's going to be sodium hydroxide. The hydroxide is the strong base, but sodium hydroxide is usually the compound we talk about. Okay, both of these in solution are going to be aqueous, which means that the HCl and the NaOH are dissolved. They, right, you're adding them to water and they dissolve. We talked about it in class where something being dissolved means it doesn't necessarily have to break apart, but sometimes it does. What do these two compounds do in solution when they're dissolved?
They switch from, or they separate.
Yes, yep, they separate, right? So we can split HCl into H plus and Cl minus. And we can do the same thing for sodium hydroxide. Okay, so we're writing that same side of that left hand of our equation, just broken up into the ions. We're representing, if we got really, really close down, look under a microscope, what would we be seeing? We'd be seeing H plus ions, chlorine ions, sodium ions, and hydroxide ions. Now, what do sodium hydroxide and hydrochloric acid do in solution? What do they form? H2O. And what phase state is H2O in? Good. And what else do they form? NaCl. Awesome. What is NaCl? What phase? Aqueous. Yep. So if we're writing, again, this right side of the equation now as what the left side of the equation looks like, what does water do in solution? Stays the same, right? This just comes down, and this is just H2O liquid. What does sodium chloride do? That splits apart, right? It doesn't actually form that compound, sodium chloride. It just kind of hangs out as Na plus ions and chlorine minus ions. So when we write a net ionic equation, we're looking at what chemistry is actually happening. Our chlorine ions and our sodium ions just hang out in solution and just create something that our water molecules can bounce off of, right? They look the same on both the left-hand side and the right-hand side of our arrow, right? You can think of the arrow as an equal sign, okay? But our H plus ions and our OH minus ions, they look different. They now look like water. They don't look like ions anymore. They look like water. So if we were to write our net ionic equation, we just get H plus ions, OH minus ions, forming liquid water. So the net ionic equation takes out any fluff of the chemistry and just shows you what's actually happening in that reaction. Yes. Yes. Yep.
So the NaCl, it's split, it's soluble.
Yes. Yep. It's soluble. It's an ion. And so you'll learn that likes dissolve likes. Sodium chloride is polar, water is polar, and so that will split. Go ahead.
So I know that there are some like elements that, I don't even remember what the word was, but they're aqueous, but they don't dissociate and they are
Yes.
soluble.
Yes.
Which is like, I don't understand how they're soluble and aqueous and still don't dissociate and how to tell which one would and which one wouldn't.
Good. So when we form sodium chloride, what is the component? What is sodium? What do we call sodium? In terms of like where it is on the periodic table. It's a metal. Yep. And what about chlorine? That's a nonmetal. So when a metal and a nonmetal form a compound, what do we call this? This is ionic, right? So this whole thing is an ionic compound. Okay, right? It's forming from an ionic bond. What about ethane here? C2H6. What is carbon? Is a nonmetal. What is hydrogen? A gas, which is also a nonmetal. Yep. So we said, I heard it first, right? This is going to be a covalent bond. If something is being held together through covalent interactions or covalent bonding, this can become aqueous, but doesn't dissolve, but doesn't break apart. Into ions. There's no ion that can form from this compound. Okay, this just gets a bubble around it, right? It gets a bubble of water. You think of carbon dioxide bubbles in your water, in like seltzer water or something. Think of ethane being in a bubble in your water, right? It just stays as an ethane molecule. It doesn't break apart into C's and H's. It just stays as C2H6. So in this case, this is something that can be aqueous, but is going to not break apart into ions.
So it'll always be just the
Mhm. Yep. Does that help?
I mean,
Does that help a little bit with how that looks like? Yep. In terms of determining what? Yes, yep. So if it's a strong acid or a strong base, it'll always break apart. Right. So if we look at HCl, right, that's technically a nonmetal and a nonmetal. But that's a classified strong acid, and so that'll break apart into solution. Yep.
I mean, all like acids and bases are covalent bonds or not necessarily.
I'm gonna say not necessarily. But that's a good point. So weak acids and weak bases, these you do not split up in your net ionic equation. And an example of this would be HF. HF is a weak acid. So if we combined this with a strong acid of NaOH, this would form water and NaF. But in this case, if we break this apart, we get H plus, F minus. These are all aqueous. I'm sorry, we don't get HF and H plus. We don't break apart weak acids. So we get HF aqueous. We get Na plus aqueous and OH minus aqueous. We get H2O liquid. We get Na plus aqueous and F minus aqueous. So what do we cancel out here? Just the sodium, right? Just the sodium looks the same on both sides. Bless you. So this becomes HF plus OH minus H2O and F minus. Yes.
Some more examples of like weak acids and bases.
So she will tell you if it's a weak acid or base. I can tell you your 6 strong acids though. So if you want to know your 6 strong acids are HCl, HBr, HI, HNO3, HClO4, and H2SO4. Anything else that's an acid will be considered weak. So like H3PO4, that is a weak acid. And then your strong bases are not as well known, but common, are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium, strontium, and barium hydroxide. I think they're both going to tell you that if it's going to be a strong acid or a strong base, they'll say, right, HClO4, a strong acid, is mixed with sodium hydroxide, a strong base, write the net ionic equation. You might have to predict your products, but she will tell you if it's going to be a strong acid or a strong base. But those are those. So if they don't see one of those and you don't recognize one of them, then it's probably a weak acid or a weak base.
Will they ever just tell you the name, like acetate, and then not the formula, so you have to figure it out?
Potentially, but acetate is one of the ones that's in your polyatomic ion chart that'll be given to you. So you just need to recognize that acetate, oh, I might not know the formula for that. Maybe let me go check my sources and see if I can find the formula for it. Yep. Same thing with like sulfate or nitrate. Those are ones that are typically pretty common, but will be on your chart. Any other questions? Yeah. So we haven't talked too much about how they stay together, but it's due to polarity interactions and strength of bond and whatnot. But for right now, you can just know that it stays together, and you'll find out later in the semester when you talk about like actual bonding and stuff, why that is. Yep. What other questions?
Example where it was something that I saw on homework where there was it multiple H's and then multiple O's, and then you had to combine them into an H2O with like subscripts.
Yep. Okay, so we're gonna do this one where we're going to. Right, we're gonna predict the products first.
Do we always like assume it would be double displacement? Or
if you see ionic bond and ionic bond, then you would assume that it's going to be double displacement, or if you see like two components in both of them, then you can assume it's going to be double displacement. Are you in Dr. Altamos's or Dr. Altman's class? Okay. There was one example that we gave where you have like, you might have like Ag solid metal and then, and we'll try this one, like we'll just show that one, right? So in this case, right, you just have metal and then you have two components left and right. This would be a single displacement because you don't have two components in each one of them. But in this case, you're going to probably assume it's going to be double displacement. Yep. Alrighty, so looking at that blue equation, what is going to be one of our products? One of them is going to be water. What's going to be our other product? What is the charge on PO4? Why 3?
On the chart.
It's on the chart, and then also from your subscript in your H, thank you. Right, we have 3 hydrogens. Hydrogen, we always know, is going to have a +1 charge. So in order to balance out that 3 minus charge, we need 3 hydrogens that are positively charged. So what do we need to do to our lithium? We got to give it 3 lithiums as well. Yep. Yep.
So you can manipulate the subscripts on the right and not.
So no, we are predicting the products. And so when we say manipulating the subscripts, we are creating a balanced we're creating a neutral compound. So we're telling our compound we need to have 3 lithiums. So we're not manipulating anything yet until we start balancing equations. And then that's when you cannot touch your subscripts at all. When you're predicting the products, you can use the subscripts that you need to create a balanced charge. But once you're balancing your reaction, then you don't touch the subscripts.
So this is like step 4 balancing.
Yes, yep, right. We predicted our products and now we're gonna balance. So now the subscripts are off limits, okay? So what do we need to do to balance this equation? We need coefficients, right? So we just said that we put 3 lithiums in our product side. So what do you think that means we need to do to our lithiums on our reactant side? We also need 3. Yep. Okay, what else does that do?
6 H's and 3 H3.
Perfect, yep. Is there anything else? Does everyone see how we balance this equation? Right, so let's go over that again. We're given that we know that our product is going to be lithium 3 phosphate. So that means we have 3 lithiums. So in order to balance those 3 lithiums on our product side, we need to put a coefficient of 3 in front of our lithium hydroxide on our reactant side. That now causes us to have 6 total hydrogens on our reactant side. And so to make 6 hydrogens, we need a 3 in front of our water on our product side, right? So we're only touching the coefficients. We're not touching any subscripts here. I gave you, I think, 13 balancing reaction problems on the practice stuff once I did. So we'll have plenty of practice from there too. Okay, and that would be an example of where you have multiple waters and you need to manipulate that a little bit. Okay, any questions on net ionic equations that help a little bit with all of that fun stuff? Yes, okay. Any other questions? Yep.
I'm not very good with like unit conversions.
Okay,
Not like the 1-step, but like the 4-step ones.
okay,
When there's like, convert from, I don't know, moles to whatever, but like it takes like 4 conversions. Or a specific amount out of the whole like equation.
yep. So just like applying moles and molecules and atoms and all that
Yeah,
stuff.
like-
Yep, okay.
Yeah.
Perfect. So when we're talking about unit conversions in terms of using the mole and we have a gram or we need to know the number of atoms or molecules in a compound, The biggest thing that we need to know is what number. Avogadro's number. Yep, 6.02 times 10 to the 23rd. I think she gives you one extra decimal, but 6.02 will get the trick done. Okay, this is very similar to a dozen, right? If we say a dozen, how many things do I have? 12. If I have a mole of something, I have 6.02 times 10 to the 23rd of it, right? So this is equal to 1 mole. 6.02 times 10 to the 23rd moles is a lot. That's right, 6.02 times 10 to the 23rd times 6.02 times 10 to the 23rd. This number is equal to 1 mole. 12 is equal to 1 dozen. Okay, that's the way that we need to remember this. Let's go over a couple of things that we know. If we're on the periodic table and we see the molar mass, what is the molar mass unit for? Or what is that in? Good. So if we're given a mass of something in kilograms, let's say, can we get to the moles of how much we have of that? Yes, we can, right? If we're given kilograms, we can convert to grams, and then we can use the molar mass in grams per mole to get to moles. Okay. Some other things that we might need to know is concentration. What do we usually say concentration is in? That big M. Molarity. Yep. What are the units for molarity? Big M, right? This is going to be moles over liter. So if we're given a volume of something, can we get to the moles of whatever that is? Yes, we can, because we can use concentration. If we're given the volume of something, can we get to the number of grams of it that we have? Yes, we can, right? Because we can go from liters to moles, and then using that molar mass can get to moles to grams. Okay, so I like to write out my units just so I can kind of see a roadmap of how I'm going to use it. So one example that we could do from this is just saying that we have okay, 26.3 grams of NaCl. And I want to know how many chlorine atoms there are. What would be your first step in trying to solve this question?
Grams to moles.
Yeah, good. We need to convert grams to moles. So in order to do that, we need to know what? Molar mass of sodium chloride. I think this is 58. But I haven't used that. Yeah. Okay, so in 26.3 grams of sodium chloride, we know that the molar mass is going to be 58.44 grams. Does that get us to how many atoms of chlorine there are? No. Right, and now we're in moles of sodium chloride. If you're in moles of something, you can kind of work any way you want. I think there'll be a big chart in about a couple chapters, maybe at the end of this chapter, a bunch of flow charts that, of once you're at moles, you can get a lot of places. But once we're at moles, we can say, okay, I now know I have 1 mole of sodium chloride. And 1 mole of sodium chloride, how many moles of chlorine do I have? We have 1, right? Because in a sodium chloride atom, we have 1 sodium ion and 1 chlorine ion. So for every 1 mole of NaCl, we have 1 mole of chlorine. So how do I get to atoms of chlorine now? Now we can use Avogadro's number, right? We can say that 1 mole of chlorine is equal to 6.02 times 10 to the 23 atoms. Okay, you can skip this middle step of 1 mole NaCl to 1 mole of chlorine if you can see that in your head, right? That's just going to be 1/1. But in some of your more complicated compounds, right? Maybe if we looked back up at the H3PO4, right? In 1 mole of H3PO4, we have 4 moles of oxygen. So maybe you just need to write that one down. But in this case, if it's 1-to-1, maybe you could just skip that. Okay, but once we know all of this stuff, would that answer our question if we get to do the math across? That would, right? So I think everyone has fancier calculators than I do, but if you don't, I would recommend doing the top divided by the bottom. I guess. I heard someone say sig figs earlier. How many sig figs do we need? 3. So if I have what are we rounding to?
So-
Good. Yep. Questions there on unit conversions? Does that help clear up your question a little bit?
Yes.
Any other questions? Yep, absolutely. All right. Give you all a minute to write it down, but I'll read it out loud at the same time. So you have 33.3 grams of HCl and want to make a 0.1 molar solution. How much volume should you dissolve your HCl in? All right, so what unit are we looking for here? We're looking for something in liters, right? Can we get there? Yeah, we can. Right, what's the first thing we're gonna do? We need grams to moles. So HCl is gonna be 36.46 grams. Can we stop there? I guess in terms of like the rest of our train tracks. Do we need any more train tracks right now? Not really, right? So we can get how many moles of HCl we need. Okay, so you have this many moles of HCl. We want to get to a 0.1 molar solution. How are we gonna find what volume we need?
5, 9, 1, 4, 4, 5, 4, right?
Let's check, right? So what are we using? What is molarity in again? Moles per liters, right? So we have 0.1 moles per liter is equal to, right? We know we have 0.91484 moles over X. So you can cross multiply and then divide. And so we end up with X equaling It is, yep, so we multiplied our x by 0.1, so we have 0.1 times x, and then we divide it by 0.1 to get liters by itself. Sorry, when it's that case, when I write it like that, I'm saying that capital M could also be written as moles over liters. Right, so you can always think of, like, I don't think of capital M, I think of moles over liters at all times. Yep. Okay, so then I end up with 9.14. 4 liters. How many sig figs? 3, so how many liters do we need? Good. Does that help with molarity a little bit? Yep. Right, and we could ask the same thing, right? I could say you have a 0.1 molar solution and you have 500 milliliters of it, right? How many grams of HCl do you have, right? You can go backwards and work that way as well. I think for both the questions that we just did, I think I have some practice problems from either last week or this week in the beginning of both of those. If you need more practice from that. Alrighty, what else?
Okay, this is gonna kind of seem a little rudimentary, but could you go over some of the basics of sig figs? Because I guess I still get a little confused.
Yeah, absolutely. So when we go over sig figs, I promise they will become second nature after a while. But when we look at sig figs, if you are adding or subtracting. What's going to be our rule? Yep, the lowest what? Decimal, yep, lowest decimal count. Yep. You want your lowest decimal. So what I mean by that is that if you have 5.10003 and you're adding 5.29, how many decimal points are we going to have in our answer? We're going to have 2, right? So we would have 10.39 as our answer. Yes. You would go to the nearest whole number, right? If this was 5.1000006. Yep, that's all it is. Right, so when we get 10.39, how many total sig figs are in 10.39? There's 4 total sig figs, but there are only 2 decimal points. Right, how many total sig figs in our second example? Just 1. If we were doing the second example, but this was now what is going to be our answer? 10. What do I need? You need a decimal point. Right, you do need a decimal point. You need that would make that 10 have how many sig figs? 2. Questions on adding or subtracting? Yep. Yep. So we are going, right? We only have like there's no decimal place after your 5, but that 5 is significant. So that makes it to have, you need at least the ones place. That means that anything in front of the ones place is significant as well, because it's accurate to the ones place. So when you add it up, you get 10. If you put a 0 and no decimal point, any of the zeros there become insignificant, right? We don't count those. But the ones place is significant, right? So we need that decimal point there in order to make that ones place significant.
But you wouldn't write it like a 10.0.
You wouldn't write it 10.0 because it's the second answer is not accurate to the tens place. It's only accurate to the ones place. Yep.
So we had like problems over like polarity and whatnot.
Mhm.
And one of them, we got like a ton of like liters or something. But we had like, it was like 3.69 grams or whatever, but the answer was like 100 and something. But the correct answer was rounded to the ones or to the tens place. Like, can you just explain how that would work?
Right, you had like 2 decimal points and then everything always had 2 decimal points.
Let me see if I can. pull
Okay.
it up.
Because you're doing, so then maybe this will help too after we talk about multiplying and dividing. So if we're multiplying, multiply or divide because I can't spell. All right, what do we do with multiplication or division? The least number of significant figures. Okay, so if we have 1.25 multiplied by 1.1, how many total sig figs are we gonna have? We're gonna have 2, right? So that might be, right, this is gonna be 2.35. I picked a good one. So what is the answer going to be? It'll be 2.4. We'll round this to 2.4. And then the same thing for division. Yep. Yep, so then you're just gonna follow your PEMDAS rules. So if you have something where it's so if we have something where it's this, we're going to first follow PEMDAS. We're going to do 1.25 times 1.1. And we would get 2.4, right? Because we just solved that. And now it's going to be plus 0.337. So now what rule do we follow? Now you follow your addition and subtraction rule. So now this would be 2.7 as our final answer, because we're just going off of what that significant figure is and what that significant figure is. Okay. I say this example with a grain of salt. If we look back at our molarity question up here, we did a lot of addition and subtraction. Your molar masses are significant for far greater than what they actually show on the periodic table. So you don't count those significant figures, right? Those are infinitely significant. But we were given 33.3. That only has 3 significant figures, and we were dividing and multiplying here. So that's why we ended up with 3 significant figures. If you do a whole bunch of stuff, like once we start doing a lot more complicated problem solving and whatnot, what I tend to do is I like to look at my question. So in my question in blue, the only sig figs that I have is 33.3. I'm going to round my final answer to 3, and that's probably going to be correct. Yeah, go ahead. Yep.
But there's like 4, like if it's other there's like 4 decimal places, right? And it says when you have the perimeter and volume, and it tells you convert to centimeters. So centimeters is 2.54, right?
Yep.
And so what would you follow? Would you follow the sig figs of the centimeters? Or
Yep. So any conversion factors, right? Molar mass is a conversion factor. Unit convert like 2.54 centimeters. That's a conversion factor. All of those are infinitely significant, which means you just go off of your starting number.
are what is it?
You would,
It's just like you have like 3, 4, 5, 6, 7 inches.
Mhm.
All right.
Yep. 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 Yep, so if you have something where you have 3.654321. Oh, I wrote that backwards. 321 inches, and you need to get this into centimeters. Right, your conversion factor is 1 inch is equal to 2.54 centimeters. This doesn't matter when it comes to sig figs. You go off of how many sig figs you have in your original number. Yep.
What if we're doing like multiple numbers with different sig figs?
Yep. So if you're saying, right, you need to find area, let's say, right? Areas, or let's say volume, right? You need length, width, and height. So we have length times width times height, and we have 3.456. This is 2.1, and this is 1.75. You have to convert all of this to centimeters, maybe kilometer, whatever, something, right? You're gonna go based off of what has the smallest number of sig figs. How many sig figs is smallest here? 2. So your final answer is 2 sig figs.
And if we were adding, it would still be.
Yep, it would be whatever
but it would
the
be
1 decimal. Yep, yep, yes, yep. Follow whatever has the smallest number of original sig figs. So you're fine if you were adding, right, or something, then you would only have 1 decimal point at the very end. Same thing for like our molarity question. If I gave you that we had 3.4567 grams of HCl and a molarity of 0.25, what one are we going to follow for our sig figs? We're going to follow the 0.25. So it doesn't matter what you do in between, you're going to end up with 2 sig figs in your final answer. Right, if you're taking your sig figs quiz for your lab, right? If you're doing stuff with lab and whatnot there, your smart worksheet, follow the original rules that we were talking about. But when you're solving OWL and when you're solving like exam questions, we can do this little shortcut here that we're doing right now. Yep, so right, if we're gonna find, we had grams and we had molarity, we need to find volume. What we needed to use, our final answer was gonna be 2 sig figs because our molarity is in the 0.25 molar. Right, so that only has 2 sig figs. So whatever volume we get at the very end is also gonna have 2 sig figs. Does that help?
Actually, quickly remind me, this is so dumb. All the rules like how.
Yep.
With the zeros, because sometimes I get confused with the counting.
Yep. So if you have, right, 0.0000, we have this one here, you only have 1 sig fig because none of these count. If we have now 2 zeros following, we now have 3 sig figs because the zeros don't count until that first non-zero number, and then they count all afterwards as well. How many do we have in our third example? You have 7 sig figs. Because our first non-zero number comes in that 10th place, so all of those zeros now are significant. If we just have 100, how many sig figs do we have? This is only 1. If we have 100 and a decimal point, we have 3. We have 1,001. We have 4.
is writing 100.0 the same thing as writing?
No, nope. So 100.0 does not equal 100 point. Because how many sig figs are in 100.0? There's 4 here. How many are in 100 point? 3.
Could you review, percent abundance?
Yep. So can you tell me what a percent abundance is? What does that tell us?
How much of 100 grams, or how much of a molecule is in 100 grams of a compound or something like that?
Yeah, pretty close. So percent abundance, is going to be how much of each isotope you have. Not to be confused with percent composition, which is how much each element makes up the compound. Right, so for percent abundance, we're just looking at one element. We want to know how much of each element we have, or how much of each isotope of that element we have. In percent composition, we're given a compound and want to know how much a specific element makes up in that compound. So percent abundance usually looks like let's do that would be a typical percent abundance question. Do you know how we would solve this percent abundance question?
Don't take the molar mass, so 12.1
Mhm.
equals, I guess, carbon 12 times X plus carbon 13 times X, or times Y, I guess they're in different percentages.
Yep, but what do we typically do instead? Good, right? So we're going to change this Y component to be 1 minus X. Right? Because the percent of carbon 12 plus the percent of carbon 13 equals 100%. So if we convert these to decimals, right, this is point, whatever this percent of carbon 12 plus point of the carbon 13 is equal to 1. So which one is easier for this question? What's the question asking for? Right, we're asking for carbon 13. So if you put X as carbon 13, then you automatically solve for what percent carbon 13 is. Right, so if we change this and we say 12.011 is equal to 12 times 1 minus X plus 13 times X. Now we can solve for X, and the X that we get is going to be the percent abundance of carbon 13. Does that make sense, everyone, why we're doing it? X is carbon 13. You can totally solve it the other way where it's X for carbon 12 and 1 minus X for 13, but you just have to do one extra step afterwards. Yep. Yep, yep. And if I just asked you for what is the percent abundance of each isotope, it does not matter which one you pick. Okay. Do you want to keep solving this one, or do we feel comfortable with getting the rest? Feel good? right? This just becomes algebra at this point. You can distribute your 12 and then solve for x. Okay. An example of a percent composition question. Um, is that you're given a compound and you want to know what your percent of a certain element is. So in this case, right, we're given glucose, we're given C6H12O6, and we want to know the percent composition of carbon in your glucose. What do we typically need for percent composition questions? We need molar mass. Of what? Good. Right, we need the molar mass of the compound and the element of interest. What else do we need? Yeah, perfect. Right, it's not enough to say 12 divided by whatever the molar mass of glucose is. You need to know that 6 moles of carbon exists in your element or in your compound. So you need 6 times the molar mass of carbon divided by the total mass of your compound. So in this case, percent comp of carbon is going to be equal to 6 times 12.01 divided by the molar mass of glucose. How would you find the percent composition of hydrogen for glucose?
1.08.
Awesome. Right, and you can do the same for oxygen. Yep. And if you found the percent composition of carbon, hydrogen, and oxygen, what should they equal? They should equal up to 100. How are we feeling? Good, better, different? Yeah. Anything other questions?
I do have to redo multiply by 100.
Yes, you would have to multiply by 100 to get to percent. This would give you a decimal. So to get the percent, you would just multiply by 100. How else are we feeling? Good? Yeah, any other questions that we might have? Okay, so I did put, right, so the rest of this is a whole bunch of balancing equations. We got a good amount of stuff in here. At the very end, I do a little bit of redox reactions. It's okay if you don't all get those fully. We only briefly talked about them in class today for Dr. Altimos. I'm not sure how far Dr. Altman's gonna go into that. But 11, 12, 13, 14, 15 on this is going to be stoichiometry and limiting reagent questions. So that's going to be something you're probably going to cover Thursday, Monday, or Thursday, Tuesday in Dr. Altman's, and then definitely Friday and Monday in Dr. Altimos's. So if you can't get to those yet, you will be able to if you do decide to do this, but these are all pretty good. They get a little bit harder as you go down between 11 and 15. Alrighty. There's no other questions. It's pretty much 6:30, so I can let you all go. But I'll hang around if anyone has any extra questions, and I'll post this along with the practice problems when I get home. Thanks for coming. Like this one? Yeah. Yes, it'll be under the office hours tab, so we'll do that. Yep.
Yeah, okay. Yes.
Is that the SI section?
Yes.
Wednesday is the day of chemistry.
Where we go there every Tuesday, Wednesday.
Oh, nice. Do you think that's helping as well?
Yes.
Okay.
It's like so good.
Yeah.
I feel like it's given to us and then he like hopes that they stay a little bit.
Ahead, yep, yep. I think it's, everything's free, so I'm like, take advantage of it. So, yeah, absolutely. Yeah, absolutely. Thank you. Have a great day. Yeah. Yeah. Let me stop my Zoom. Let me stop my Zoom, so.